Good morning, students. So, in the last class, we discussed about that quantum numbers and their significance. Okay. So, in the today's class, we are going to discuss about rules for the filling up of electrons in the different orbitals. Understood? So, in that, listen. So, before going to that, I'll explain how to find out the quantum numbers, and based on that quantum numbers only, these electrons going to fill up. Okay. So in the last class I told you if it is a s orbital, the energy of s orbital must be like 1s, 2s, 2p, sorry, 3s and so on for s orbital. If the shell increases, energy also increases. Next, for 2p also, 2p is greater than 3p, greater than 4p, sorry, less than 4p, etc. For 3D also, 3D is less than 4D is less than 5D, etc. 4F also, 4F is less than 5F. Means the one which is having the greater n value, that is having greater energy. So remember that. Okay. So if you know this value, then you can easily go on how to write the electronic configuration. So we will go with that. There are four rules are there to fill the electrons in the different orbitals. Among those, the first one is Pauli's exclusion principle. Okay? Pauli's exclusion. Okay? What is the statement of this Pauli's exclusion principle? So yeah, no two electrons in an atom have same set of all the four quantum numbers. Understood? No two electrons in an atom have the same set of all the four quantum numbers. That means what? If two electrons are there in the same atom, okay, I mentioned in an atom, in only one atom, if two electrons are there are four quantum numbers and they cannot have the same value for all the quantum numbers. So I'll take the example here. For example, which one it is? Okay. 2p you take. 2p orbital. Okay. So in this 2p orbital, n value is 2. Correct? So here I take 2p3. So here it is 2p1. Here it is 2p2. Here it is 2p3. Here it is 2p4. Understood? So if we write the n value, m value, everything value for this, so I will take for 2p1, I write the one electron here. Okay? For 2p orbital, I write one electron here. So for this orbital, n is equal to 2. M is equal to, for p orbital, 1. M is equal to, this electron is presenting -1 state and the spin ms is minus of. Next, 2p2 means this electron is here. Here, n is 2, l is 1, m is same, m is 0 here. And the ms is of course, sorry, plus of this is not minus of. For the third electron, 2p3, correct? So n is same 2, l is also same, but this m, magnetic quantum number is how much? plus 1 for third electron. And the spin is, of course, it is plus half. Next, if you consider fourth electron, it is paired up. So here, this is 2. For p orbital it is 1, here it is minus 1, and the spin is minus 1. So students, remember here, in all these cases, n is same, l is same, m is different. But spin is same among these. What I am telling, no two electrons in an atom have the same setup on the 4 quantum numbers. Here 3 are same. 2 1 off, 2 1 off, 2 1 off. That is same. That is what is the principal, azimuthal as well as spin quantum numbers are same for these 3 electrons. But the change in what? Only the magnetic quantum number. That is what the statement of Pauli's exclusion principle. At the same time, no one electron in the same atom, no two electrons in the same atom can have the same set of quantum numbers. So remember, you just leave these two, consider 2p1 and 2p4. So among these two, 1 and 4, this is same, this is same, this is also same. Both principal quantum number, azimuthal as well as magnetic is same. But here, plus half is there, here minus half is there. There is difference in spin. This is also a quantum number. So this is what exactly the statement of the Pauli's exclusion principle. Understood what this principle tells about? No two electrons in an atom have the same set of all the 4 quantum numbers. And this is the example for that. Understood? Okay. So the next one is this is first one. And the next one is second one. So second one is of Bach principle. Second one is of Bach principle. Understood? Here. So alpha principle tells about what? So in an atom or in a ground state, okay, the filling up of electrons takes place in the increasing order of the energy. Understood? So orbitals are there, different orbitals. In that different orbitals, the energy is going to fill up the energy. The filling up of electron takes place according to what? The increasing order of energy means lower, followed by somewhat higher, higher, higher. Okay, so that is the statement. So at ground state, of an atom, electrons fill up takes place. Electrons fill up takes place in the increasing order of energy of an orbitals. This is what? Of Bach principle. At ground state of an atom, electron fill up takes place in the increasing order of the energy of the orbitals. So SPT of orbitals are there. I write the certain roots, after 1s we choose 2s, after 2s 2p, 2p 3s, 3p, before 3p that is 4s. So that is what the increasing order of the energy. How to find out that is here. This is 1s, this is 2s, 2p, 3s, 3p, 3d. 4s, 4p, 4d, 4n. Next, 5s, 5p, 5d, 5n. And 6s, 6p, 60 and 7 is 70. So students, this is the orbitals present in the entire periodic table. How the electron fill-up takes place, this is the order. So listen, the order follows like this. Initially this is 2s. Okay. Later on, right? Okay. So listen. This is the order. 1s, after 1s 2s, after 2s 2p, next 3s, 3p, 4s, next 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6d, 7s, and the last one is 5f, 60, 70. This is the correct order of energy. The least energy is 1s, the most energy is the 7p orbital. This is greater in energy, this is smaller in energy. If we write the order here, so I won't write less than greater than symbol here, I simply write the increasing order from 1s orbital to 7p orbital. Initially what it is? 1s. Next 2s. Next 2p. There. This is 1s after 2s. This from this direction. 2p after 2p. 3s. Next 3p. Next 4s. Next. So after 3p, 4s. Next 3d. Okay. 3d. Next 4p. 5s, 4d, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 60, 7s, 5f, 60, 70. This is the correct order of filling up of electron takes place. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 4p, 6s, 4f, 5d, 6p, 7s, 5f, 60, 70. You write 7s here. 7s, 5f, 60, 70. Once this is like a set. Okay, this is how the filling up of electron takes place. So in this, what it is going to tell? Electronic configuration. And remember here students, s orbital, the maximum electrons to be filled is 2. P orbital, maximum electrons to be filled is 6. Okay, and d orbital, maximum electrons to be filled is 10. And next, f orbital, maximum electron to be filled is what? 15. Remember, what is the formula for this? This is the number of electrons in an orbital is equal to 2 into 12 plus 1. Okay, remember students, initially I did in the shell number of electrons is equal to 2n square. In the orbital, in the subshell, the number of electron is equal to 2 into 12 plus 1. L means the azimuthal quantum number. Understood? So I just rub this and after that I show. Okay, so listen here. K shell means 1s orbital, L shell means 2s 2p orbital, M shell means 3s 3p 3d orbital, and N shell means 4s 4p 4d 4f orbital. So students, for this, okay, so the formula to the total number of electrons. Total number of electrons is equal to how much? 2n square. N value is 1, 2, 3, 4. So according to this formula, in K shell, maximum number of electrons is 2. In here it is 8. Here it is 18. Here it is 32. That's we already calculated in the yesterday's class. Now we have to calculate the number of electrons in the orbital, like s orbital, p orbital. So this is for what? Shell. This is for subshell, means orbital. So total 4 orbitals are there. The formula is 2 into 12 plus 1. For what? The number of electrons. Here for s orbital, L is equal to 0. So according to this formula, 2 into 0 plus 1 means 0 plus 1, 2 ones are 2. So I completely write 2 into 0 plus 1. So that is 2 into 0 plus 1, that is 2 electrons. So in s orbital, 2 electrons. Next consider p orbital. For p orbital, L is equal to 1. So here it is 2 into 1 plus 1. So that is 2 into 2 plus 1. That is 3 2s are 6. For p orbital, maximum number of electron is 6. Next. Okay. For d orbital, L is equal to 2. So next, according to this formula, 2 into 2 plus 1. So that is 2 into 4 plus 1. That is 5 are 10. For d orbital, maximum number of electron is 10. Next, f orbital. So this f orbital means L is equal to 3. If L is equal to 3, according to this formula, 2 into 3 plus 1. That is 2 into 6 plus 1. So 7 2s are 14. So the maximum number of electrons in this orbital is 14. We just fill up here, students. Here we consider only maximum number of electrons is 8. Here 2 orbitals are there. In s orbital, 2 electrons. In p orbital, 6 electrons. Total 8 electrons. So this is the formula to calculate the number of electrons in subshell. This is the formula to calculate the number of electrons in the main shell. Understood? So according to this, the electronic configuration. So writing the electronic configuration takes place. Wherever the s orbital is there, whether it is 1s, 2s or 7s, s orbital means maximum electron is only 2. p orbital means maximum electron is 6. Once the 6 electron filled in p orbital, we next jump to 3s orbital. So here 1s. After completion of the 2 electron, we need to take 2s. After completion of the 2 electron, we need to take 2p. In 2p, we need to fill up 6 electrons because the capacity is 6. So after completion of the 6 electron, next energy level 3s, here 3p, again 6 electron, next 4s, here 3d. In 3d orbital, so it takes place how many electrons? 10 electrons. Until the 3d electron completely filled, we cannot go to next orbital. Okay, that is 3d, 10, 4s, so next 4p something, or 4p1, 4p2. If 4p completely fills, next 5s. If 5s fills 4p, 4p fills 5p, 5p fills 6s, 4f. Similarly, the highest energy is 7p. Understood? This is all about what? Aqua principle. Next one is rule of maximum multiplicity. Rule of maximum multiplicity. What it tells about? Okay, students remember. So maximum multiplicity. Okay, so in the orbital, if you take the for s orbital, we are writing like this. If you take the p orbital, okay, so here if p1 electron is there, then it will fill up like this. So p2 is there. Instead of pairing up, we are writing here. If p3 is there or p4 is there, instead of writing, remember here, if p4 orbital is there, instead of writing like this, okay, we are writing like what? Initially, they fill it first like this, 1, 2, 3, next this one. This is the correct way of writing. So this is explained why we choose to write like this, because this is explained by this rule. We need to fill up the electrons in this manner. Initially, they are filled singly, followed by the pairing. So here, Hund's rule of maximum multiplicity. Here for s orbital, they get paired up. In p orbital, it is like that. Okay, because this is of different energy. If we take 2s and 2p. Listen. 2s is here, 2p is here. Initially, this is completely filled because the filling takes place according to increasing order of energy. Means 2s will fill up first, followed by 2p. But among 2p, 3 orbitals are there of same energy. If the same energy orbitals are there, then the electrons are singly filled first and later pairing up takes place. This is what a statement of Hund's rule of maximum multiplicity. Okay? Among the orbitals of same energy, the electrons singly fills first and later pairing up takes place. So this is what the statement of Hund's rule of maximum multiplicity means. If the orbitals are having the same energy, like px orbital, py, pz, similarly if you take d orbital 1, 2, 3, 4, 5. So d6 electron is there assumed. In this d6 electron, initially 1, 2, 3, 4, 5. All the orbitals are filled up singly first. Later, the 6th electron is paired up here. This is what? So, because this is of what? 3D orbitality. All are 3dxy, 3dyz, 3dzx. All are in the approximately same energy. Understood? If they are having same energy, then the electrons are, what they will do? They get initially, singly filled initially, followed by fading out. So this is Ohm's rule of maximum multiplicity. Only overall, how the question will arise here? They only ask statement, state Pauli's exclusion principle, state alpha principle, state Ohm's rule of maximum multiplicity. Statement is enough for you. Okay. So and the last one is n plus l rule. The most important rule here. L plus L. N means principal quantum number. L means azimuthal quantum number. So what are the conditions here? Smaller the n plus L value, lower is the energy. Okay, smaller the n plus L value, lower is the energy. Next, second one, if n plus L value is same for two orbitals, then the orbital having smaller n value, so that is having small energy, is having least energy. These are the conditions. There is no statement here. So it is simply a sum of the principal quantum number as well as azimuthal quantum number. Here the thing is what? Smaller the n plus L value, lower is the energy. Understood? If n plus L value is same for two orbitals, then the orbital having smaller n value, that is smaller principal quantum number, that is having the least energy. So students, I'll consider these two first. One is 2s. Remember, in 1s and 2s, here n value is this one. 1. S value for this, n value for this orbital is 0. Here n value is 2, L value is 0. So here n plus L value is how much? This is the n plus L value. Here it is 1, here it is 2. So smaller the n plus L value, lower is the energy. So 1s is having less n plus L value, so it has the least energy. So the filling up of 1s orbital takes place first. Next, 2s. So we did with what? 1s. So consider 2s, 2p. So students, here 2s we already discussed. So 2p, here principal quantum number n value is 2. For p orbital, L value is 1. So it is 3. Correct? So that's why after this 1s, 2s, 2p is going to fill up the space. Next I write 3s, 3p. After that 4s, so I write 3d only. 4s, remember this. So here the n value is 3 and n value for s orbital is 0, that is 3. N value is 3, n value is 1, that is 4. Here n value is 4, n value is 0, that is 4. Here n value is 3, n value is 2, that is 5. But here, remember, so from these examples, you can easily consider these two applications. So if then the n plus L value is same, here the n plus L value is same, 3 and 3, then what happens? So here, for two orbitals, then the orbital having smaller n value. Among these 2p and 3s, which one is having the smaller principal quantum number? Means this one. 2p. 2 is the smaller value compared to 3. That's why this is having least energy. If the n plus L value is small, no matter what, it has the least energy. If n plus L value is same, understood? Then one which is having least n value, principal quantum number value, that is having small energy. So here also 3 is there, 4 is there, 4 is there. So students remember, after 3s, 3p, 3d, they are the same shape. Even though 4s orbital fill-up takes place first rather than 3d. Why? So according to the n plus l, here, this is 4, this is 4, this is 5. Even though principal quantum number is 3. So that means n plus l value is more, then the energy is more. If n plus l value is less, then energy is less. If they are same, then only the second application, sorry, the second condition follows. So this complete electronic configuration is based on n plus l only. Means based on principal quantum number and azimuthal quantum number, and at the same time, in that we can represent, of course, this configuration in principal as well as azimuthal quantum number. So in the arrangement, magnetic is also there, spin is also there. Understood? So this is all about the 4 quantum numbers. So 4 rules to write the electronic configuration and rules to fill the electronic configuration. What you need? You need only, what is the statement? What is Pauli's exclusion principle? No two electrons in an atom have the same set of 4 quantum numbers. That means, so in a same atom, if 2 or 3 electrons are there, those electrons cannot have the same set of all the 4 quantum numbers. They may have 3 equal, 2 equal, 1 equal. They cannot have all the 4 equal in number. Next, Aufbau principle. So at ground state of an atom, electrons fill-up takes place in the increasing order of the energy. This is the energy, increasing order of energy. Next, Ohm's rule of maximum multiplicity. Among the orbitals of same energy, the electron singly fills first and later pairing up takes place. This is Ohm's rule of maximum multiplicity. They may ask also, write the conditions for n plus l. Okay. The first one is smaller the n plus l value, lower is the energy of the orbital. Next, if n plus l value of the orbital is same, of any orbital, 2 orbitals are same, 2 or 3 orbitals, then the orbitals having the smaller principal quantum number value having the least energy. Okay, these are the examples. Why 4s comes first than 3d. Okay, so this is all about the rules governing electronic configuration. So the next one is stability of completely filled and off-filled configuration. Next one is stability of completely filled and off-filled configuration. So students here, stability of completely filled and off-filled configuration. So remember, completely filled means if I take the s orbital, I'll write off-filled first, next completely filled, next incompletely filled. Okay, so this is S orbital you. This is p orbital. S. Check here. This is S. This is p. Okay. Next. D. Yeah. Okay. So this is SPD of ion. So students, what are offered? This one is offered. So all the three single electrons in the orbitals are offered. This is offered configuration. This is stable. Offered. So completely fit means they get cleared up like this. Okay. So then comes to this is also these two are stable. Okay, this is also stable, this is also stable, this is highly stable. Understood? So students, incompletely filled. Of course, in S orbital, there is no incompletely filled. If one electron is there, that is half filled. If two electrons is there, that is completely filled. So in S orbital, there is no incompletely filled configuration. One is half filled, another one is completely filled. Because if you fill up only one electron, it is half filled. If it is two, completely filled. When it comes to p orbital, if only one electron, incompletely filled. Two electron, incompletely filled. Three electron, then it is half filled. That is stable. Until two electron, it is unstable. Unstable. Incompletely configuration means this is unstable. These two are stable. So this is stable. So fourth electron, 2p4, unstable. These are incompletely filled configuration. If another one electron, that is completely filled. So I write here the four possibilities. One is this, another, these four are the incompletely filled configurations of p orbital, and these are unstable. They are not stable. Here also, incompletely filled, incompletely, incomplete, or filled. Then it becomes stable. Next, incomplete. Then another one electron, then that is stable. Here also same. Single electrons are there without any electron, that is incompletely filled. 1 to 6. This is half filled, stable. Incomplete. Understood? So this is our report. What? So listen here. In this P3 and P6 are the stable configuration. Here D5, D10. Here F7, F14. Except these configurations are unstable configuration or incompletely filled configuration. Only these two. P3 are filled, P6 completely. P5 are filled, D10 completely. F7 are filled, F14 completely. Except these configuration, the remaining configuration tells about what? Incompletely filled orbitals, and they are unstable. And remember students, that's why to become stable, okay? So to become stable, what happens? Some arrangements change. So if I take chromium, So chromium atomic number is 24, and you take copper, in that sense its atomic number is 21. If you write the electronic configuration, 1s2 followed by 2s2, 2p6, 3s2, 3p6, correct? And 4s2, 20 over and 3d, 4, 24 pins. This is the configuration. So here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Okay, so students, I'll consider this one as argon of atomic number 18. So this configuration changes to argon 4s1 3d5. This one changes to argon 4s1 3d10. Because students, when this is 3d4 configuration, it is like this. When it is 3d9 configuration, it is like this. Of course, this is a stable configuration 4s2. If we remove one electron, then also it is stable. If we remove one electron, then also it is stable. That's why, due to the high stability of 4s1 and 3d5 and 4s1 and 3d10 configuration, the configuration of chromium and copper in the ground state follows this configuration rather than this, because of the stability of half-filled and completely filled configuration. What is the reason for this half-filled and completely filled configuration? Why they are stable means because they are in the same orientation, means there is no repulsion between them. In all the orbital, the here p orbitals are there, listen. Like this, p orbitals are there. Okay, so in these p orbitals, among any one orbital, two orbital electrons are there, then this orbital try to attract those electrons towards themselves. Then there is a fight between the orbitals to get an electron. Then they become incomplete, highly energetic. Okay, when they are in a high energy, they are not stable. They are unstable. So if all the electrons, all the orbitals having at least one electron, then they are happy. Of course, he is also having one electron, he is also two, and I am also having one electron. They are stable, like that. Like kids, they are fighting. Understood? So this is what the stability of half-filled and the completely filled configuration, and this completes the chapter structure of atom. Thank you.